Hello everyone. Come, let's go with automatic generation control. Other name of automatic generation control called AGC. In this control system, we have two areas of system. One is single area system, another one is two area system. Before that, we have to see basic role of AGC. AGC to maintain desired megawatt output of generator, to assist in frequency control of large interconnection, to keep net interchange of power between pool member at predetermined value. In a single area system, there is no tie schedule to be maintained. Thus, the function of the AGC is only to bring the frequency to the nominal value. This will be achieved using the supplementary loop, which uses the integral controller to change the reference power setting so as to change the speed set point. The integral controller gain represent K1 needs to be adjusted for satisfactory response in terms of overshoot setting time of the system. Although each generator will be having a separate speed governor, all the generator in the control area are replaced by a single equivalent generator and the automatic load frequency control for the area corresponds to this equivalent generator. One area system or single area system having dynamic response of it. Now we are going to study the effect of disturbance in the system derived. Both loss of generation and loss of load can be simulated by imposing a positive or negative step input on the variable power load. A change of the set value of the system frequency F0 is not considered as this is not meaningful in real power system. From the diagram is straightforward to derive the transfer function between one area to another area. In order to calculate an equivalent time constant, this can be done since for realistic system, the turbine controller time constant Tt is much smaller than the time constant. Single area system having two classification. One is static analysis of uncontrolled case, another one is static analysis of controlled case. Static analysis of uncontrolled case in the sense generator synchronized to a network of very large size. Frequency is independent of power output of individual generator, that is individual network. Directly proportionality between reference setting and turbine power. Static analysis of controlled cases. Generator synchronized to a finite size network. Reference power setting is unchanged. For a constant speed changer settings, static increase in turbine power is directly proportional to troop in static frequency drop. This is dynamic response of single area system I taught previously. Then we have to see the next topic of multi-area system. In an interconnected multi-area system, there will be one automatic load frequency control loop for each control area. Each control area means located at the ECC of the area. They are combined for the interconnected system operation for a total change in load of variation of connected power. Differentiation of connected power. The steady state consider are two area system depicted. The two secondary frequency controller, one is AGC1 and another one is AGC2, will adjust the power reference value of the generator participating in the AGC. In an N area system, there are N controllers AGCI, one for each area. A common way is to implement this is a proportional integral PI controller. Then this response has been shown that the load frequency control system possesses a steady state, inherently steady state error for a step input. Applying the usual procedure, the dynamic response of the control loop can be evaluated so that the initial response also can be seen for any overshoot. For this purpose, considering the relatively larger time constant of the power system, the governor action can be neglected. Treating it as instantaneous action, then the turbine generator dynamics also may be neglected at the first instant to derive a simple expression for the time response. Then interconnected operation. Power system are interconnected for economy and continuity of power supply. For the interconnected operation, incremental efficiencies, fuel cost, water availability, generation limits, tie line capacities, spinning reserve allocation and area commitments are important consideration in preparing load dispatch schedule. Flat frequency control of interconnected stations or consider two generating stations connected by a tie line. For a load increment on station B, the kinetic energy of the generator reduces to absorb the same. Generation increases in both the station A and B. Generation increases both the station A and B. The frequency will be less than normal at the end of the governor response period. The load increment will be supplied partially by A and partially by B. The tie line power flow will change thereby. If a frequency controller is placed at B, then it will shift the governor characteristics at B parallel to itself. The frequency will be restored to its normal value, reducing the change in generation A to 0. Assumption in analysis. The following points are made in the analysis of the two area system. One is the overall governing characteristics of the operating units in any area can be represented by a linear curve of frequency versus generation. Second thing, the governor in both the area start acting simultaneously to changes in their respective area. Third, supplementary control devices act after the initial governor response is over. The following time instants are defined to explain the control sequence. While the initial governor response is the same as for the previous case, the action of the controller in B will force the generation in area B to observe the load increment in area A. When the controller begins to act at time 3, the governor characteristics is shifted parallel to itself in B till the entire load increment in A is observed by B and the frequency is restored to normal. Thus, in this case, While the frequency is regulated on the hand, the tie line schedule is not maintained on the other hand. If area B, which is in change of frequency regulation, is much larger than A, then load changes in A will not appreciably affect the frequency of the system. Consequently, it can be said that flat frequency control is useful only when the small system is connected to a much larger system. Then dynamic response, let us now turn our attention during the transient period. For the sake of simplicity, we shall assume that two areas to be identical. Further, we shall neglecting the time constant of generator and turbine as they are negligible as compared to the time constant of power system. The equation may be derived for both controlled and uncontrolled cases. There are four equations with four variables to be determined for given PD1 and PD2. The dynamic response can be obtained. Even though it is a little bit involved, for simplicity assume that the two areas are equal, neglect the governor and turbine dynamics, which means that the dynamic of the system under study is much slower than the fast acting turbine governor system is relative sense. Also assume that the load does not change with frequency d1 equal to d2 equal to d is 0. The frequency of the damped oscillation is given by, since hand f0 or constant, the frequency of oscillation depends upon the regulation parameter r. If low r gives high k and high damping and vice versa. We thus conclude from the preceding analysis that the two area system, just as in this case of a single area system in the uncontrolled mode, has a steady state error but to a lesser extent, and the tie line power deviations and frequency deviations exhibit oscillation that are damped out later. Thank you.